Okay, so this is going to be an interesting talk. We're going to talk about the protein engineering tournament, which will be presented by Chase Armour.
Thank you. So hello, everyone. I know it's been a long day of really incredible talks, but the good news is that you've made it. This is the final contributed talk of the workshop. So we'll see if we can't send it off on a high note here. My name is Chase Armour, and today I'll be talking about an exciting new project called the Protein Engineering Tournament. So the entire field of computational protein design can be separated into two primary actions: to predict and to generate. In the case of prediction, we start with a protein. This could be a sequence or a structure, and the goal is to predict a set of properties about that protein, with these being a few examples. In the case of generation, however, we start with a desired list of properties, and then we generate a sequence which is meant to possess them. Now, I believe the grand challenge of the entire field is the development of intelligent systems that can perform both of these actions across any domain of protein function. And to get there will be a cycle composed of two steps. One, we develop new methods, and two, we benchmark them. And by benchmarking, we can learn what works, and we can collectively iterate and improve. However, what I would argue is that the greatest limitation facing our field is not the ingenuity of researchers to develop new methods, but the inability of researchers to properly benchmark them. So how do we do benchmarking today? Well, in the case of prediction, we have data sets. So this data set maps sequences to some properties. We then have our model predict those properties. We compare it to the ground truth, and then we have our benchmark. In the case of generation, where we're creating that which has never existed before, what we really want to benchmark is experiments, which is to say that we condition our model to generate a sequence, and then we bring this out into the real world. We express it, and we characterize it to assess its properties. And so the challenges that are facing our field are, in fact, the limitations that are facing both of these benchmarking efforts. So in the case of prediction, we have data sets that notoriously can have small numbers of data points. They often lack complexity, having only single-point mutations or maybe covering only one property of interest. And lastly, they tend to have low diversity and just cover a sparse amount of the total protein functional space. But it's in the case of generation that things get even worse. For the most part, many computational labs have no in-house experimental capabilities, meaning they're entirely reliant on collaborations, which, as the panel had kind of alluded to, aren't always focused on benchmarking. And secondly, which I think is the biggest limitation of all, there exists no standardized experimental benchmark for generative protein design. So for all these reasons, it's fairly clear that the field of protein engineering is in need of a unifying benchmark, something that can allow us to collectively learn, improve, and iterate towards solving this grand challenge, which is why I'm excited to be telling you all a bit about the Protein Engineering Tournament, which is an open science benchmark for computational protein design methods. So the structure of the tournament is meant to be a reflection of the field itself, and as such is separated into two sequential rounds. The first in silico round is focused on prediction, and the second in vitro round is focused on generation. So in the in silico round, we're going to have a list of challenges which are stratified across supervised, which provide training data, and zero-shot, which do not. In the case of our supervised challenges, researchers will be provided with a never-before-seen data set that is mapping protein sequence to protein properties. And the objective will be to predict the unseen properties on a list of held-out sequences. Once all these submissions are made, we'll be able to make leaderboards across each one of these challenges. The scoring metric will be challenge-specific, but you can expect Pearson and Spearman correlation to be popular within the in silico round. And while the in silico round will be open to anyone with a computer, it will be the top performing teams that get to move on to our in vitro round. So here, once again, we're going to have supervised and zero-shot challenges. And in our supervised challenges, we have never before seen data. However, the goal of these challenges is now to generate a list of protein sequences which satisfy some challenge-specific objective. So if we look here in this example, we're asking the researchers to maximize activity while being above some threshold of stability and expression. And so the researchers will create this top list. They'll submit their, let's say, top 100 sequences. And what we're going to do is we're going to take every submitted sequence, we're going to order the DNA, we're going to express the protein, and then we're going to characterize it experimentally in the laboratory to assess all of these properties. And using this experimental data, we're then going to generate leaderboards for each one of the challenges. And by summing up across the leaderboards from the entire tournament, we'll have our tournament leaderboard, and we'll identify our protein engineering champions. So there's going to be three key deliverables that are offered to the community at the end of each tournament. The first of these leaderboards, this is what provides a quantitative assessment of each participant's method. There's going to be all of the data that was introduced both in the in silico and the in vitro round, including our newly generated experimental data. And then the third deliverable is actually the one that I'm excited about the most, but it touches on a topic we haven't quite covered. And so to understand it, I have to make the first exciting announcement of the presentation, which is that the protein engineering tournament will be powered entirely by Cloud Science Laboratories. And so everyone here in the audience who is not familiar with Cloud Labs, please allow me to introduce you. So Cloud Labs are automated science facilities that allow researchers to run experiments directly from their laptop. And they do this by use of symbolic lab language. So this is a programming language that allows you to define an experimental protocol as a sequential list of unit operations. So for example, in our transfer function, we'll have a source, a destination, and an amount. In incubate, we have our temperature and our time. For fluorescence, we have our excitation and emission wavelengths that we want to measure. And so once you've written this protocol, you can then submit it to the cloud laboratory, at which point it's automatically executed by a combination of humans and robots. And the moment the experimental data is, the experiment is finished, all of the resulting data is uploaded for your analysis to your laptop. And so this is the instrument readouts, this is environmental data, timelines. Every single pressure trace from the aspirations and dispense that happened are now at your fingertips. And very excitingly, we also get this video of the experiment. And so this is an experiment I myself ran. What you're watching here is the cell-free expression of the luciferase enzyme, followed by a luminescence readout in that plate reader there. And so what Cloud Labs really allow us to do is encapsulate experiments as code. And once you're able to do that, there's an incredible array of benefits that come. First and foremost, we can now share experimental protocols the same way that we share software. So imagine a future in which a researcher publishes a paper, and in it they include a link to the cloud protocol that they ran. And then you could use this and at the click of a button, reproduce all of their experimental results. But excitingly, it goes beyond just reproduction. It goes towards generating new data. So once you have this cloud protocol, you can now put new protein designs through it, for example, and benchmark new methods. And so that's why I'm so excited about this third deliverable for the tournament, which is going to be the cloud protocols for every single in vitro assay that we run. And so to make this clear, what this means is you don't have to wait for the next tournament to start benchmarking your new methods. Instead, you can develop a new method, generate new designs, run it through this cloud protocol, and now you have new results. And so in the long term, what this means and what we really envision is that since each tournament is going to introduce a new set of cloud protocols, we foresee an ever-expanding corpus of cloud science and open science protocols that will slowly cover, ideally, all domains of protein function. And so I believe if we want to fulfill the promise of this workshop of combining computation and experiments towards solving this grand challenge, I believe this is a rough sketch of what that might look like. So for the second exciting announcement, we have just finished our pilot tournament. So this was with a small, tight-knit group of about 7 teams, some of which are here today. So I firstly want to say thank you to everyone who was involved. This really helps us learn all of the challenges along the way to make sure we can offer a really excellent experience for our first official tournament. And all of the data from that tournament, the data sets that we offered in the in vitro and in silico rounds, as well as the newly generated protein designs and their data are going to be available next week on the alignbio.org website. So please check out AlignBio. I'll show that link again. In addition, I just want to emphasize that this has been the result of a community effort that's spanning academia and industry alike. And at the heart of this is the Align to Innovate nonprofit founded by Erica De Benedictis. And you should really check out a lot of the incredible work they're doing. I think it's very relevant to everyone in this room. And so lastly, I would like to leave everyone with the final announcement of the presentation, which is that our first official protein engineering tournament will be coming in early 2025. And so if any of this has been exciting to you, either as a future participant or a future organizer, I really encourage you to go to alignbio.org. There you can sign up to be the first one to know when that tournament is online. And you can reach out to me, of course. I'll be here to answer any questions you might have. So thank you.
Okay, that was a great way to end this. We do have one last sponsor to present, and then we'll